Alright, AS Chem, this is a video to help you study for Unit 8 Celebrational Learning on Thermochemistry. And so I'm going to go through these problems to give you guys some explanations. I've posted the answer key online. I'm going to post this video alongside it so that you guys have help if you need anything. Please do the study guide, take a look at this video for any help with it, check your answers, let me know if you have any questions, and hopefully you guys are going to do great. So with that being said, let's go through this. And so the first kind of, I think, 10 questions in this study guide, I have made multiple choice. Pretty similar to some of the multiple choice you will see on the celebration learning. So hopefully this helps you review some of the same concepts. And so number one, it says a metal spoon is heated and placed in cold water. What happens? And so how you want to think about that, right, is we have a spoon, it's heated, we put it in water, right? So this spoon is hot. And so if we put it in the cold water, what's going to happen? Well, we know that the hot spoon will give heat to the cold water, right? We can say the Q spoon, right, heat of spoon, is going to be released. It's going to give off heat. And that heat is going to go to the water, right? Q is equal to negative Q. That's basically what this question is asking. It's asking you, do you understand the idea of heat? That heat is a transfer of energy, that the heat given off by the spoon is the heat given off, or the heat gained by the water, right? And so here, what happens, the spoon certainly does get colder, the water does certainly get hotter, but the correct answer is C. The water heats up and the spoon cools down. Both of these things are happening. The heat that the spoon gives off is equal to the heat that the water gains. This obviously isn't true. There is no temperature change, and it's also none of the above. So it's C. So Q is equal to negative Q. Very simple concept. Genuinely, you don't even need to know negative Q is equal to plus Q to just know that, yeah, what's going to happen is water heats up, the spoon cools down, right? There is a transfer of energy. All right, if you touch a container where an endothermic reaction is occurring, it would feel, so remember, this is just basically asking you, do you know the definition of endo and exothermic? Where endo is like enter, and therm is heat. So this is a reaction where heat is entering into the system. And so, you know, if this is your system, that's the container, heat is entering in. Remember, that's going to feel cold, because if you have heat entering in, well, where is it getting that heat from? It's getting it from you. And so you're going to feel cooler. Endo heat is entering the system, so you feel cold. And so the opposite is an exothermic reaction where heat is exiting the system. And so if heat is exiting the system, it hits you and you feel warm, right? So endo and exo, remember those definitions. Number 4 asks you to know the definition of this sentence: the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, right? This is very specific, right? It's saying, okay, specifically for 1 gram of a substance, how can we raise the temperature exactly 1 degree Celsius? That's the specific heat capacity, right? Not the heat capacity. The heat capacity is, generally speaking, you know, how resistant is a substance to changes in its temperature? How much heat do we need it to raise its temperature? But specific heat capacity gives us how much heat do we need specifically for 1 gram for 1 degree Celsius. That's heat capacity, or the calorie and the joule are units of energy. They are not, don't confuse those. It's also not none of the above. Cool, okay. And so then this takes me to number 5, which of the following are units of heat? And so what I want you to know is that the calorie and the joule, okay, this is kind of a select all that apply question. The calorie and the joule are the units of heat. Okay, so don't mix that up with, for example, units of temperature, which is here, which are the Kelvin and Celsius. Again, what students so many times mix up is they mix up temperature and heat. They're like, oh, the heat, we measure the heat of the system. And it's like, no, you can't measure the heat of a system. You can measure the temperature change of a system and therefore calculate heat change, but you don't really measure heat, right? So don't mix up temperature and heat. Right? Heat is Q, temperature is T. These are very distinct things. Temperature is a measure of the average kinetic energy. You don't need to know that, right? But fundamentally, it's a different thing compared to heat, which is not energy, it's a transfer of energy. Now we're getting more into like 8.1 and like some of the basic definitions I gave us. But, you don't even need to know all that. Just please, heat is different than temperature. Their units are different. Cool. Okay. Number 7, which of the following are exothermic? And so, again, this is heat exiting, heat as a product. And then lastly, remember heat given off. That's another way of putting it, right? And so if heat is given off, delta H is a way of thinking about the heat of a system, right? And so that's going to be negative because we're giving it away. It's like money. When we give away money, it's negative money. And so here, which one of the following is basically asking you about thermochemical equations. Can you identify endo versus exothermochemical equations? And so what we see here is burning propane. Well, we have a negative delta H. And so that's going to be exothermic, right? Because negative delta H, heat given off, right? Yeah, this is clearly exothermic. And yeah, this is a combustion reaction. And we know that combustion reactions are exothermic. But continuing on, right? Are any of the other ones exothermic? Well, here we have ice melting. If you melt, you're going from a solid to a liquid. You need to have heat for that. Heat needs to enter, so this is endo, so that isn't true. Decomposition of potassium chloride. Well, let's see, the delta H here is, so that's endo again, right? Because heat is entering the system, so that one isn't exo. Here, neutralization, we have heat as a product. Oh, yeah, right, that is exo. Yeah, heat as product. We're giving off heat at the end, and so that's also going to work. Photosynthesis, here we have heat as a reactant, and so that's, again, endo, right? So it's going to be A and D for those. All right. Which process shows an increase in entropy? Remember, entropy is the disorder of a system, if we're speaking plainly and simply at the high school general level. And so when we're talking about increases in entropy, right, remember sloppy, right? Positive entropy is going to be, basically, if you have positive delta S, right, then that means that it's becoming sloppier, right? Positive delta S means that it's becoming sloppy. Its disorder is increasing. And so where is disorder increasing? Well, let's see, freezing water, what we're doing is we're turning something where the particles are spread out into something where they're not, where they're clumped up. So now that's not true, right? That's not going to be more disorder. But boiling water, right, we're taking it where particles are like this, right? They're spread out, but now we're going to make them even more spread out. And so boiling water, actually, that is going to increase disorder, right? What else increases disorder? Well, one molecule becoming 3. Right? Basically, we're taking like something that might look like this, and we're making it into 3 separate pieces. Yeah, right? It's kind of like you're cutting up a piece of paper. Yeah, you're making everything more messy, right? And so that's also going to work. 2 becoming 1. Now you're actually increasing order there, right? You're making things less sloppy. You're consolidating. That's not increasing entropy, and then none of the above also doesn't work. So cool. B and C. Very nice. And so that's basically asking you, do you know the definition of entropy? Number 9 is asking you if you know the definition of delta G, right? Gibbs free energy. A reaction is always spontaneous. Remember, go in, right? So if it's negative delta G, it's going to go, it's spontaneous. Going, like the Southerners. And so it's going to be B. On a side note, one of my students taught me the other day the phrase, raise hail, praise Dale. Interesting, Southerners. I love that. Truly a motto to live by. Basically, he got a question right, and it was just like, raise hail, praise Dale. I was like, dang. Well, what a phrase. So anyways, you can quietly mouth that to yourself if you get a question right on the celebration of learning, or if you feel like you killed it. Quietly. Speaking to some of my boys who will take this way too far. But continuing on, go in, number 9, 10, which combination of delta H and delta S always leads to spontaneity? You could memorize this little chart that I showed you guys, and you could, but I'll be honest with you, I don't have that chart memorized. Some of you guys have shotgun memories and you like to memorize everything, and that's great for you, but I don't like doing that. I like to have I like logic. But yeah, you could just memorize that little chart and use it here. But I like logic, right? And so here's my logic here. Delta H losing heat, right? Basically, losing heat, that is spontaneous. That is something that happens in the universe. Anytime you have heat, I mean, think about yourself right now, right? your body is losing heat, right? Like that's a spontaneous process. Generally, heat likes to diffuse, to spread out. That's spontaneous. That's going to happen normally, ordinarily. Right? If you heat up a room, right, it's just going to decrease in its heat over time, right? Heat always spreads. That's how it is. And so negative delta H, heat spreading out, that's a spontaneous process in the universe. Also, the other thing I told you, remember, is entropy increasing, right? Sloppiness increasing is also spontaneous, meaning the world is falling apart, right? And you know that. If you leave out a turkey, it's going to rot. If you yourself, right? We're all getting older. We're all going to die. I mean, I know that's not a cheery thought, right? But like, that's just the reality of life in the universe. Anyway, not to get too philosophical. I know you guys have been reading Camus recently, and fun times, huh? But point is, right, negative delta H is spontaneous, positive delta S is also spontaneous. And so these are the two things that are spontaneous that lead to a negative delta G. You could also kind of puzzle this out, right, by being like, okay, well, delta G is equal to delta H minus T delta S, right? And it's like, okay, what's the conditions which always lead to this being negative? Well, if this first thing is negative, and then we minus a positive, right, minus a positive will always be negative, right? And so, yeah, this is actually true, right? If we have minus delta H and positive delta S, remembering that T is always positive and therefore it doesn't really factor into here, minus a positive term here, right, is always going to be negative. And so this is the situation where we always have spontaneity. And so here, negative delta H, so delta H being less than 0, so these ones can't be true. It has to be delta H being less than 0 and then delta S being greater than 0, right? So it has to be B. B is our correct answer here. Cool. Okay. So continuing on. Just make sure I didn't miss anything I want to tell you guys. Cool. Okay. That's all looking great so far. I don't think I missed anything. So let's continue on to some of these kind of free response questions. And so here is just simple conversion. Please, I need to make sure that you guys know how to convert things. Otherwise, you're going to die in future chemistry courses. And so, right, basically here, how do we go from calories to joules, right? Remember, we take what we're given, and this is what we want to get to, right? We have 250 calories. We want to go to joules. And so then here we got to multiply by a fact in fraction form. This is our fact. We put it in fraction form. We put the unit that we want. On top, we put the unit that we want to get rid of on bottom. Calories cancel, and you will be left with 1046 joules. There you go. So please make sure you know how to convert units. Then we go on to number 12. How much heat is required to raise 150 grams of copper by 20 degrees Celsius, where C is equal to 0.385 joules per gram degree Celsius? This is a question where heat is question mark, right? And we know that the equation for heat is Q is equal to MC delta T. Here, this is mass, right? So the mass of our object is copper. We're trying to raise it by 20 degrees Celsius, so delta T is equal to positive 20 degrees Celsius, and then C is that. So all you got to do is plug it in. Quite simple. 150.0 grams times 0.385 joules per gram degree Celsius plus 20 degrees Celsius for delta T, you will get 1155 joules. Now, of course, we only have 4 sig figs here, 3 sig figs here, 3 sig figs here. So you should really have only 1160 joules as your final answer. Now, again, if you're off by 1 or 2 sig figs, that's fine. But please don't just do 7, 8 sig figs. Of course, we couldn't really do that for this one, but don't do infinite number of sig figs. Then I know that you clearly know nothing about sig figs. All right. So going on to here, this time we have heat, we have mass, we have delta T, but now it's asking us for C. What is the specific heat? And so remember, Q is equal to MC delta T, as we were saying. We want to solve for C this time, though, so I'm going to take M and delta T, divide it on both sides, and we will get Q divided by M times delta T is equal to C. And so Q, right, this is Q, this is M, this is delta T, and so we get 950 joules divided by 500 grams times 10 degrees Celsius is equal to C. And if you put that in your calculator, you will get 1.9 joules per gram degrees Celsius is equal to C. Cool. Going on to number 14, fill out the following heating curve, right? Remember, this was 8.5, very easy lesson. All you have to do is just remember what's happening here. And so remember, this is how I fill out a heating curve. I think, okay, well, at the bottom of temperature, right, we're always going to be going from solid to liquid to gas. And so here, it's a solid, here it's a liquid, here it's a gas. Now, remember, we flatten out at the phase changes. So here we're going from solid to liquid. Here we're going from liquid to gas. And now I'm going to fill it out a little bit more with a couple more details, right? This is a solid, but the temperature is increasing. So this is the solid being heated / heating up. This is the liquid being heated / heating up. And this is the gas being heated / heating up. Now here, what's the name of going from a solid to a liquid, right? Think about ice. If you take solid ice and you turn it into liquid water, that's called melting. And so this is melting. And then liquid to gas. If you have liquid water, you turn it into gas. That's what we call vaporization. And so, yeah, so that fills it out quite well, right? So you can see it's pretty easy if you just think, okay, at low temperatures we're solid, higher we're liquids, and then we go to gas, right? You can fill out these things, remembering that the flat parts are phase changes. And then you'll only have to think of, okay, well, first we're going from solid to liquid, that's called melting, then we go from liquid to gas, that's called vaporization. Again, you can shotgun memory it, but again, you know, if you just know solid, liquid, gas, which you know from real life, you could just kind of reason it out. Cool. Okay. So going on to number 15, these are your delta G is equal to delta H minus T delta S. And these are hard problems. I get it. But you could do it again with logic. So first thing to note is that delta G is equal to delta H minus T delta S. Right. So that's kind of the equation that we want to use here. Now, for these, remember that it's ultimately going to depend upon the values of delta H and delta S. So when you're making an argument, right, and I'm telling you here, based on delta H and T delta S, right? Remember that T is positive always, so that's not really going to factor here. So it's going to be what these values are. If whatever these are, they're going to affect the sign of delta G. Now T can be important. It's just it's going to act as a scalar. It can make this term here really big in comparison to this, or it can make this term really small in comparison to this. So T is just a scalar. It's always positive. It scales us up or down, but it doesn't change signs. And so first we got determine the signs of delta H and delta S to see if T even matters. Cool. Okay. So what I always do here, therefore, is I think through, okay, well, what's delta H? And then I think through, okay, well, what's delta S? And so here, right, we see energy is at the end. And so remember, if energy is at the end, energy is a product, this is a exothermic reaction, right? So energy as product. And here, delta S, well, okay, we have 3, we have 4 particles of gas, and we consolidate it down to 2 particles of gas. What's happening is that the sloppiness of the universe is increasing. And remember, if sloppiness is increasing, it's positive, but here it's decreasing, and so we're actually decreasing the sloppiness of the universe. And so 4 particles to 2, sloppiness is decreasing. And so then based off of that, I'm like, okay, well, let me try to determine the sign. Delta G is equal to delta H minus T delta S. Actually, let me not write that out because I don't have that much room. I'll give you guys more room under celebration. But here, we're going to say delta G is equal to delta H minus T delta S. Now, so delta G is equal to negative delta H, okay, minus T minus delta S, right? Now note that this is all one term. These are being multiplied together. And so if we simplify that down, we can say it's negative delta H minus T delta S. Okay, so again, we're taking that negative term, multiplying negative delta S times T, you get negative T delta S. Now note, we have here negative, right? So delta G is equal to negative delta H minus is a positive T delta S. And so we're taking a minus and we're adding a positive. So what we get here is going to depend on which one's bigger. If this is bigger, the positive is bigger, then we're going to have positive delta G, right? And so if t is big, this term is big, and therefore it's going to be bigger than this side, and therefore we're going to have positive delta G. Versus if t is small and this is small, this part is going to overpower this part, and we're going to have a negative at the end, right? You got to just kind of logic it out for yourself, but this is the idea here. If, I guess I should say, depends. Sine of delta G depends. If t big, and I should go here. I should actually probably write this out over here because I don't have enough room. Sine of delta G depends. If t big, and therefore t delta s is big, delta G will be positive. Whereas if t small, and therefore t delta s is small, delta G will be negative. So delta G is temperature dependent. And so that's how you would do that one. Now, this is my explanation. This would be sufficient for a celebrational learning. Now, I did give you an even bigger explanation on the answer key. I was trying to be really thorough there so that no one will write like a sentence on their celebrational learning and say, well, your explanation was small too, right? Here I gave a pretty good explanation on the celebrational, or on your study guide key. I also gave a pretty good explanation. Now, you don't have to be as thorough as I am in the study guide. Another reason why I made it really thorough is try to explain it as much as I can to students. But again, ultimately, I will say, this is a hard topic. You really have to sit with it, right? That's how it is with hard topics, right? You're not going to get it from somebody else just talking at you. You have to try to describe it to yourself. You have to try to describe it to others. That's just how it works, right? I've had the most amazing teachers and professors in the world, and yet still, I had to sit with topics, right? Like, that's just how life works. So, hopefully I'm giving you the tools you need, but you got to try to explain this to yourself. And I know that's going to be hard, right? I know you're going to be frustrated, and you can still do it. So, give it your best shot. Do practice it. You can do this. You just got to practice it. So, okay, so that's this one. Now let's go on to this one, the second one, and this is actually the exact same idea here, right? Again, you want to figure out what delta H and delta S are, and here again we have delta H being negative, right, because energy is a product, and here we have 2 particles, and we're turning them into 1, and so again, actually, here delta S is decreasing, right? The sloppiness of the universe is decreasing because we take 2 things and consolidate it into 1, and so we are in a very similar situation. Again here, it's similar to 15a. Sine of G depends, right? It's actually the exact same situation, right? Because delta H and delta S are the exact same thing as an A, right? So sine of delta G depends. Now, I didn't do this on purpose. This is just what these problems turned out to be like. But yeah, sine of delta G depends. And so if this term is big, then this is going to be positive. If the positive term is big, delta G is going to be positive, versus if this term is small and therefore not as important, the negative term is going to win out, and therefore delta G will be negative. So I'm just going to write that here. But yeah, it's the same logic. Cool. Okay, so again, if you want even more practice, take a look at the ones that we did on the slides. Take a look at the 3 that we did for your practice problems. I'll hopefully give you a better kind of opportunity to do this, or some more chances. But cool. Okay, continuing on, let's go on to number 16. Number 16 says, write a thermochemical equation for each of the following processes. And so remember, for thermochemical equations, there's kind of 2 options for how to write things out. You could write it out with delta H, or you could write it out as energy as a product or reactant. I'll do both for you guys. And so let's do option number 1. Solid sodium hydroxide dissolves in water, and we have sodium hydroxide solution, NaOH aqueous. And in that process, we also absorb 44.5 kilojoules of heat. So what the heck is going on? You can write this out in kind of actually a number of ways. I will say on my key I did a little bit differently, but here, honestly, this is probably the most accurate way of doing it. And you just kind of say like H2O over it to say like, okay, we're basically just dissolving. Now, I actually, in my key, I wrote it as a plus H2, and you can do that, right? It's kind of basically a chemist, a trained chemist sees, oh, solid to aqueous, the H2O is dissolving it, but I know you guys don't have that eye yet. But yeah, so you could do it anyway, right? Like in my key, I wrote it like this, right? And that's okay. You could do it like that. You could also just do it like that. Anyways, point is delta H is equal to positive 44.5 kilojoules per mole. So that's one way of doing it, where we say delta H is on the side, right? And remember, we're absorbing, and so we're taking in. So that's option number one, or you could also do option number two, which is, write out the equation the same way. But here we have energy as a product, or sorry, as a reactant, right? We absorb it in order to do this, and so we can write, I guess I should have left myself a little bit more room. It's almost like, okay, if we take this and we also take in this much energy, then we can do this process. And so here it's endothermic, and so we're gonna have it as a reactant, versus here it's gonna be exothermic, and so we're actually gonna have it as a product. And so, yeah, but anyways, two options, right? You could do it like this, where you have delta H showing the energy, or you could have it like this, where you have it as a product or a reactant. Either way. But cool, okay. I've also added on one more thing here, which is to do a little bit of stoichiometry, a little bit. And so here it's saying, once you've written that out, calculate how much energy needs to be absorbed in order for 15 grams of NaOH to be dissolved in water. And so what we're saying here is, okay, well, 1 mole of NaOH is going to require 44.5 kilojoules of energy. But what if you have 15 grams, so we got to think through, okay, well, 15 grams of NaOH, how many moles is that? Well, 1 mole of NaOH is going to be equal to the molar mass of NaOH is 40 grams. And so, okay, well, this is going to be approximately 15 divided by 40, 0.375 moles. Now, for every 1 mole of NaOH, we give off positive 44.5 kilojoules of energy. And so we don't have 1 mole, so we're not going to need that many moles of energy. We're only going to need about a third of that. And so 15 divided by 40 times 44.5 is going to be approximately positive 17 kilojoules. Now, moles cancel. And so, yeah, does that make sense? Yes, it does make sense, right? Because again, like we were saying, this is approximately 0.375 moles. We said that for 1 mole, you need 44.5, but if you only have a third of that, you're gonna need about the third of the energy. And so that makes sense, logically. Cool, okay. So let's do one more, and then I'll do the rest for you guys in the afternoon, because I gotta get ready for my third period. Here, and this is a little bit of a more standard kind of chemical equation for us, we have solid magnesium, and so we're going to take magnesium, solid, we're going to react it with hydrochloric acid, HCl, and when we do that, magnesium chloride, so MgCl2, and hydrogen gas, H2G, are produced, along with the release of 144.6 kilojoules of heat. And so what we can do is we can say, okay, well, so we're going to release 144.6 kilojoules per mole. And so I know that kind of got to the end of it here. But yeah, delta H is equal to negative 144.6 kilojoules per mole. So that's one way of writing it out, right? That's option number one. Or you could also write it out like this, where exact same idea, right? We have the same equation. But the only difference is, along with the release of heat, right? Basically, it's exothermic, energy is a product, so you can write 144.6 kilojoules at the end. Cool. Now, one thing to note, I don't know if this is balanced. Here it was obviously balanced, but here, let's see. mg, the 1 and 1, but we have 2 Cl, so we've got to put a 2 here, and then we have 2 H's actually. Okay, so that's good. So there we go. So now it's balanced. Now I don't think that actually matters here, but it does, like, it doesn't matter for the second part, but you do need to have these balanced, okay? So when we write a thermochemical equation, it has to be a balanced thermochemical equation. But so continuing on, let's see, this is saying if we have 25.5 grams of Mg with an abundance of HCl, how much heat are we going to release? Well, 25.5 grams of Mg, how many moles is that? Well, 1 mole of Mg is equal to 24.3 grams of Mg. So actually we have just about 1 mole, right? So actually it's going to be very similar to this. And so 1 mole of Mg is going to release 144.6 kilojoules of heat. And so here we're going to have, let's see, if we do this multiplication, we're going to get approximately negative 152 kJs. And that actually makes sense, right? Because again, we release 144.6 if we have 1 mole of Mg. Here we actually have a little bit over 1 mole because 1 mole is 24.3 grams. We have a little bit over that. And so it makes sense that we give a little bit more than 144.6 kilojoules of energy. And so that's our final answer here. Cool, okay. So I'll cut this video here. I'll make a part 2 for you guys in the afternoon. We only got a couple more questions. So hopefully that helps you guys out though. Stay tuned for part 2.